So welcome to today's class. Let me start off with some announcements. The specification for the group project and task 3 have been updated. So download the most recent version from the COSC website. Then concerning the group project, try to contact your teammates. And if there are difficulties, send us an email, preferably in the next 24 hours. We might still make minor adjustment with respect to the groups for the group project. And then there will be a lab style class on recurrent neural networks in the October 18th class, and that's taught by Navid. So might be good to also read the task 3 specification before the lab on the 18th. And then, okay, the background is the Lake of Clouds in Michigan. So today's program is Raunak will teach a lab in preparation of the group project. Then we have the Group G group homework credit presentation. And then I will continue the discussion of similarity assessment, a topic we just started at the end of the last lecture. So Raunak, you can go ahead with your lab.
Okay, let me share my screen. Okay, can everyone see my screen?
Yes,
we can. Okay, thank you. Okay, so today I'll be going over what to do for your group project. I'll be giving a very brief introduction to geospatial analysis using Python. It's something that I do for my research. So I'll be going over things very quickly. If you don't understand something or if you need further clarifications, come to me during any of my office hours and I'll help you out. So first of all, if you have not used any kind of geospatial data before, let me give you a very quick introduction to the two types of data that are usually present. What you'll be using in your group project, the earthquake data set, is a vector. Vectors are geometries, right? So when you open, for example, your Google Maps and you see the road networks or you see traffic details and anything like that, those are all vectors, and those are what you will be working with here. And vectors are represented as essentially three types, right? So the most basic unit of the vectors is the point, the XY point, latitude, longitude, or any other kind of GPS Cartesian coordinates or any other kind of coordinates. Now those points can be grouped together to form lines. Multiple points can be grouped together to form polygons, and so on and so forth. The vector data can be very easily grouped or graphed into various smaller regions to make calculations easier. Vector data is also much it's very easy to store. It's much smaller in size. It's much easier to process using simple mathematical tools. A lot of vector information you can take a pen and paper and calculate it yourself. Now, the opposite of vector, let me give you an example of what vector data looks like in practice. On the left, you see basically the inner loop. These little points are essentially intersections of roads, and all the lines are road networks, both walkable road networks and street, vehicular road networks. So, and that's all combined together into forming this constellation-like figure that you see on the left. On the right is another combination of a vector with a raster. You see the underlying base map is of Houston. once again, downtown in Houston, like the inner loop Houston, where you can barely see UH downtown. And overlaid on top of that are the zones where Hurricane Harvey back in August 2017, where it flooded over a certain limit. So this is what a raster data would look like. So raster is essentially pixel data, like pixel level data. So any kind of like JPEG image that you see would be raster. But what is more important in geospatial data is like the JPEG image that you would see, every single pixel has a particular calculated value. Like it might be like, I don't know, like I say here, it might be color, like ground color, it might be height above sea level, it might be temperature data, wind velocity, any other kind of measurement. So on Google Maps, when you see satellite view, the images that you see, although they are not always from satellites, they might be from overhead aeroplanes. Those are raster information. On the right, the little the playing animation that you see is a satellite imagery from the GOES 16 satellite managed by USGS and NOAA. It shows valley fog, like fog early in the morning, evaporating as the sun comes up in the New England area, in the northeast of the US. So going back to what our group project is going to deal with, I recommend using Python because most of the demo that I'll be using will be using Python, and a lot of like the easier libraries are in Python, but you can also use R. R can do like almost everything that Python that I'll be showing you today Python does. R is also very strong and I would say comparably quick for some of the more complicated kernel density analysis calculations and grid making that you might need to do. The fundamental thing is that both R and Python for their geospatial analysis rely on two core libraries, GDAL and GOS. GDAL is a geospatial data abstraction library. It is an extremely powerful geospatial library. Almost no matter what you'll be doing in geospatial analysis, you will come back to like GDAL tools. So even in Python or in R, no matter what you're using, if you're using Shapely, you're using GeoPandas or whatever you're using, the underlying library that they will be using is GDAL. So if you are if you're comfortable with like Python and if you're comfortable diving deep into it, you might not need to use the wrapper libraries that I'll be showing you today. You can directly use like the GDAL functions, which will be quite fast, especially if you're doing a lot of analysis. Both Python and R use like wrap on top of GDAL, similar to how Python uses NumPy. And NumPy relies on a bunch of low-level C libraries, and then Python wraps on top of it, which is why NumPy is super fast compared to doing the calculations using core Python. Similarly, using GDAL directly will make your operations faster. So the Python packages that we will be primarily be using, obviously, if you want, you can use different packages from these, but primarily GeoPandas, Pandas, and NumPy are going to be your bread and butter. For visualization purposes, you might be using Seaborn, you might be using basemap of matplotlib, basemap, like I said, Seaborn, and there are a variety of different visualization libraries and tools. If you have trouble finding one, come to me, I'll help you out. If you have trouble finding a visualization library in R, once again, come to me and I'll help you. I would also highly recommend setting up an Anaconda environment for this purpose, because these Python's dependency chains can go out of control very quickly. Like you will lose your mind. And it is also possible because some of these dependency chains rely on older versions of libraries. It might mess up your your direct Python installation in some cases. So always I recommend, if possible, set up Anaconda, or if you don't want to set up Anaconda, set up a local Python environment and install everything in there, just so that you don't completely mess up your your installed Python packages, which I have done, and I will tell you, it is a mess to deal with. So now, going back to your actual project, what will we be doing? So you will be given a data set of earthquakes information showing time, latitude, longitude, magnitude, and depth. So let me bring up the page over here. So this is the kind of data that you would receive, right? You would have latitude, longitude, you'd have depth, and you would have magnitude from your earthquake. So what do you need to do? Given all the data that you have been given have been clumped together into 2-month batches. So they say, for example, January 2020 till February 2020. And the data that you'll be given have been clamped into just the contiguous US. So like the lower 48, so to speak. And all other like earthquake outside of that has been removed. You have also been given earthquakes of magnitude 2.5 and above only. This is to cut out like all kinds of like noise, because if it's below 2.5, you'll get fracking as showing up. Though fracking also shows up above 2.5, but a lot of like lower fracking won't show up. You will get like mining explosions. You'll get demolition information. For example, the building collapse in Surfside in Florida would show up if you go for magnitude -1 to 0 to 0.5. I think that would show up as well. So just to avoid that kind of noise, you'll be given 2.5 and above only. Now, after that, you can do what you need to do is figure out which locations within the contiguous US the earthquakes are clustering together. What are the hotspots? That is which regions have more earthquakes than the other locations, and the earthquakes are persisting. So if a certain location, say for example, Central Texas, is suddenly getting like a mass of earthquakes, then you should be able to, like, what you have to do is you have to figure out which of these locations the like a large number of earthquakes are showing up. If you have, for example, if the entirety of the US was given, then you would see a lot of earthquakes showing up in Alaska, in Hawaii, also in Puerto Rico. But if we are because we are clamped to contiguous US, you'll see a lot of earthquakes showing up in the Pacific Northwest, right? In the Cascadia Fault region, Seattle, that region, also in California. You know, obviously you'll see a lot of earthquakes showing up in California. You'll see a lot of earthquakes showing up also in the middle of the US, near the Texas area, due to fracking or due to other geological purposes that I'm not very clear of. So those are the things you have to discover. Like, so in a batch of like January to February, you divide, you find out like which locations have a lot of earthquakes, and then you shift the batch to February, March, and then you see like, again, you see the same thing, like what are the locations that have like a large number of earthquakes, and then you plot like hotspots of like which regions have like a large number of earthquakes popping up, and then you keep doing this for month after month after month, and you'll see a pattern popping up. Like, look, some locations have like large number of earthquakes, some locations don't. Some locations may have seasonality, especially if the earthquakes are fracking oriented in origin, then you might see seasonality because maybe some companies don't do fracking in the winter, maybe some companies don't do fracking only in like autumn or fall or whatever. It doesn't matter. You'll figure out like if there's any seasonality, what are the locations and regions and things like that. And the better a job you do of like identifying these changes in hotspots, the better your group project will be, and the higher scores you'll get, and the higher points you'll get. So we have, let me show you. Okay, so So this is what like discovering a grid would be like. So you take all the earthquakes that have, then that in the CSV files that have been given, then you create a density estimation of those. You divide it into grids of like some particular value, and then you estimate like how many points fall within that grid, and how this changes month after month after month. So which are the high values, which are the low values, things like that. So I'll be showing you a demo today, but I'll not be showing you how to do exactly this. I'll be showing you how to do this using a kernel, using a Gaussian kernel. And you can adapt that. And so what I'll be showing you today is slightly more complicated. You can adapt that to make it easier and without using like a Gaussian kernel and a bandwidth. And you'll find out like you'll be able to show like how the hotspots are popping up. And once you have like all the locations where these hotspots are, then you can show them changing month after month after month, and then you can write about how they are changing. Why do you think they're changing? Things like that. Okay, so let's move on to a demo. I hope this is visible. Let me full screen this. Okay, so let me zoom in a little bit. I hope this is clearly visible to you. So ignore, like I've imported a bunch of libraries. These are not always necessary for your purposes, but these are essentially all the libraries that you'll ever need for this. You probably won't need geocoders, and you probably won't need TQDM, but the others are fairly common geospatial libraries. Okay, so first let me show you how I got the data. Some of you are asking, like, since the link that is posted in the document, the group project document, does not actually let you download like month after month after data of the data. So the way you get it is USGS has their own API, and using that API, you can download like data from I think 1990 to like the current date, to like today, up to I think an hour before. So this is how you get the data, right? Show you how it runs, and then you use this function. So I'll be getting 2018 data in your group project. You'll be given data from August or March or something around August of 2020 till September of 2022. So today I'll be giving, for this demo, I'll be getting data from 2018. So I'm running this and I'm getting all the data from here. So one of the things you need to be wary of is that USGS limits the collected data to 20,000 points only. Now, because I've limited this to magnitude 1 and above instead of 2.5 and above, as you will find in your data. So some of these will be above 20,000 and USGS will fail. So you won't be able to use that. So you see the data has been downloaded, like all of these. All of these won't be full. Some of these will have no data because the data has been because there's been over 20,000 points limited requested, then USGS won't return anything. So after that, what we do is we take the data, then we filter it for only within the US. Now, in this case, I'm filtering it within the entirety of the US, not just within the contiguous US. The work that you will be doing, it will just be limited to the contiguous US. So what this means is that you will have data from Alaska, you will have data from Hawaii and other US locations around the world. So yeah, and because there's a small try, except because some of the data some of the data files will be blank. So after once you have that data, what does that filtered data look like? We drop all extraneous values. We have time, latitude, longitude, depth, and magnitude. You'll find in the group project documentation what all of these values mean, what are the extent of the values and like why we use some of them. So next, what we do is, because we're using GeoPandas, we combine the latitude and longitude into a point value so that we can plot them. So this is what we do. Ignore the warning. It doesn't matter for you. Once we have converted them into a point, let's just plot it using using the simple world plot function from GeoPandas. Oops. My apologies. I forgot that this was to stop. Whatever. What you would see in this case is a very simple. Let me show you what you would see. Yeah. So you would see if that plot worked, because I think I'm not running it in Anaconda, so it failed. So if it worked, you would see something like this. So you can see that like the values are concentrated in the US, Alaska, and Hawaii, right? But this won't be the case for your data. Your data will just have the contiguous US. So once that's done, what we next need to do is just make a simple plot of all the latitude, longitude values and do a simple density plot just to see where all the values are concentrated. So doing that, because the value is pretty large, it takes some time. OK, so this is a seaborne plot. Obviously, you don't see like the US plotted in the background, but you can see that what the density of values look like. And this is just for your quick overview of like what latitude and longitude the values are concentrated around. So what you can see here just by like data exploration is that there's a lot of points in Alaska, sorry, a lot of points in Hawaii, a lot of points in Alaska, a lot of points on the West Coast, California and Seattle and the Cascadia region, and some points in near the Texas region. So this is just like a very quick overview, but you shouldn't rely on this, right? And this is the entire data set. Next, what we do is we filter the data set for values of magnitude 2.5 and above only, and we plot it again. So you can see this has been filtered, and then we plot these values as well. And you can see that the number of values has gone down quite a bit. So for 2.5 and above. So what this means is that like Alaska and Hawaii still have a lot of values. But once you restrict it to 2.5 and above, you lose a lot of values. You can see it from here, lose a lot of values in the contiguous US. So here, that is something to be kept in mind. So your threshold for detecting earthquakes has to be much lower for contiguous US as opposed to the Alaska and Hawaii as well. So next, what we do is we set up a grid using NumPy mesh grid. So you can you don't have to use NumPy mesh grids. You can use a very fixed number of grids. You can do, for example, like a 100 by 100 grid, for example, a very basic 100 by 100 grid instead of like an equal area grid as NumPy does. But I did this so that you'd be able to get a better view of what it looks like. So you sort the values of latitude and longitude so that you get the entire range, and then you mesh it up. You create a grid of all the values in there, an equal area grid. You might, like I said, in your case, you might not do this, or you might do this, or you might use something else altogether for your grids. So next, once you have like your x and like x-axis and y-axis grids, that is your longitude grids and your latitude grids, you need to combine them, right? Because otherwise you just have like a series of x values and a series of y values. Then you combine them into a grid, Next, this is something that once again you might not do. You create a kernel density estimation using scikit-learn, right? You create a kernel density metric, a Gaussian kernel density metric using the Minkowski parameters and the ball tree. So for this first example, we use intentionally we use a very low bandwidth for our kernel density estimation, so that it tries to fit the density like very closely, right? This is a bad idea because most of the contiguous US does not have like this. Like if your bandwidth is too low, it's not gonna show you like anything really good. Absolutely. So like if you fit the data and then you train the model on this data, I'm not going to run this right now because this might, depending upon on the machine that you're running, take a long time. Like for me running this, I ran it on a laptop with a Core i9 9880H using the GPU NVIDIA 2080. So it's a strong enough laptop. Still, it took me close to around 5 minutes to do. So depending upon what you're running it on, it might take you much longer. If you want, you can run it on online on on Google Cloud, uh, if you want, but that's not guaranteed to give you like uh, faster time for doing this. So once I have done this using the very low bandwidth kernel density metric, and I've filtered for remember this data is working with the filtered data, right? So I have filtered for magnitude 2.5 and above only, and then I'm running this. And once you plot this, let me show you what you see. Oops, bad idea. Essentially you won't be seeing anything, right? The map would be almost completely empty in this case. It's my bad because I already ran it with the higher bandwidth values, like a bandwidth of 5, to show you what it would look like. Because for the low bandwidth, it wouldn't really show you much, but for the very high bandwidth, you can see that what it would show you is something like this. So you can see like it shows you for a particular month, it shows you like very high density values in Hawaii, very high density values in Alaska, and median density values in spread out across the contiguous US. So once again, in your case, you would not be doing this. What you would be doing is you'd be creating a grid and you'd be plotting that grid itself. What I did here, just to show you like what the ideal case would look like, is use a kernel density metric to plot the values and to show you what the density is. Now, this is for 1 month alone. So let me show you. This is for the month of, okay. Yeah, this is for the month of 2018-8. So this is August 2018, just for that month alone. So what you would be doing is you would be using the data that we've given you, which is like a combination of like 2 months, and you'd be running this. You'd be creating a grid this way or some other way, and then you would be estimating how many of your values fall within that grid using kernel density or some other form of density estimation for your hotspot discovery. And then you would be plotting that value just for the contiguous US. Now, once again, you can do all of this in R as well. Most of the visualization is almost similar, but you'll be, instead of using MPL toolkits, you'll be using ggplot. For kernel density metrics, there are kernel density libraries in R as well, but there are also tools that would divide like instead of using NumPy mesh grid, you can use other grid functions that are available in R. And then you overlay your grid on top of all the values. So for example, you see that this is a very large grid, right? This is a grid of like 20 by 20 longitude, which is fairly large. So you can use a grid like this, or you can subdivide it into much smaller grids, and then you have to subdivide it into much smaller grids, and then you estimate how many of your values fall within that grid. Once again, using kernel density or any other kind of density estimation technique. Manual counting is fine because the CSV values would be given. Like each batch would have roughly 600 to 800 values. So if you do manual counting, which is like exhaustively count how many values fall within your grid, it should be fairly easily doable. Right. So yeah, that's it for me. So if you have questions, comments, come to me during my office hours. I will help you understand. If you have trouble understanding like what exactly you have to do for your density estimation, for your hotspot discovery, you can come to me. Like your high density, for your high density, what kind of grid you would need, how many values you would need. These are things that you have to determine. But if you have trouble understanding, like if you have trouble implementing any of these things, come to me. I will help you out. Well, also, I would recommend using Python, but once again, if you are using R, I won't stop you for any of this. So that's it for me. If you have any questions, if you have comments, you can ask now, or you can ask during office hours, like I said.
So we have any questions or comments?
I had a question.
Sure, go ahead.
Will this demo be available to us, like in the Teams folder, or?
Yes, I'll make it available. But just be careful. If you have trouble installing all the packages, some of these can be kind of annoying. Ask me. But yes, the demo will be available. The demo will be made available on Teams. Yes.
So can you show this grid you had before?
Yes.
You had a simple grid.
Yes.
So because we haven't covered much hotspot discovery, correct, yet? Okay. So that's what we call is naive density estimation, correct? So you just count the number of objects, but then you could also use the grid information and grow hotspots, correct? Like you identify contiguous regions where the value of where the count is above 4 or something like this, and then you put them on the map, correct?
Yes. So for example, this would be a hotspot in that case.
And then, well, but then you have also the kernel density estimation, correct? So that was not so very clear from your presentation. So is this an alternative method?
Yes, but I would, yes, once again, I would recommend first doing this kind of naive grid before trying to use kernel density estimation for this purpose. But yes, you can use like the standard density estimation techniques that are available for this purpose. Like you can use Gaussian density estimation or any other kind of like the exponential or top hat. Yeah. Sorry, go ahead.
But then you could, the problem is, okay, so if you use the kernel density estimation, then conceptually now you get a continuous function, correct? So it's a function where where the density is above a surface, correct?
Yes.
So well, in this continuous surface, identifying hotspots is not so easy, correct? So we have the
Yes.
continuous density function now, and you want to now identify regions where the density is above whatever, some number 1.22, correct?
Right.
So well, you could try to develop some algorithm, but that's really challenging, correct? But the other thing you could do is you again use a grid, correct? And you just use the center of the grid cell, and you just get the kernel density estimation value for that, and then you can grow hotspots like the ones you have seen here.
Yes. So yeah, you can do that using, like I showed you, the mesh grid. So the grid that you use, if you consider instead of gridding the entire area, if you just grid like center, like Dr. Eick said, the median of each grid, and then you train your kernel density function on that grid, on the center of that grid, then you can use a cutoff value, like to do what Dr. Eick said. So you have for some range of values to see what looks good and what doesn't look good, what tells you a good story and what doesn't tell you a good story. So you can use kernel density based on like the center of each point and do it that way as well. Yes.
Can either use the center or the intersection point. Can you go back to the grid again?
Yes.
So then to give you some idea, because at the end you want to get hotspots, correct? Because if you just plot the points of the earthquake, it will be hard to see anything, especially, okay, or it's hard to judge, well, is this more dense or less dense, correct? So,
yes.
so which means, so you use a threshold, let's say we use a threshold, let's use a threshold 3, okay? So then we have, okay, and then there are different ways to do that, but you just look for seed objects, correct? So this seed object, like this 6 is above 3, correct? And then you can grow the hotspot by just adding neighbors to it. And you can have different definition of neighbors, but you can just say north, south, east, west, or you could say, well, the one in the northeast is also a neighbor, correct? So you basically, okay, try to identify seed objects, like we have this 3 in the corner, correct? But this 3 in the corner, we try to grow, but nothing happens, correct? Because, well, you just get the 3 because there are no neighbors to add, correct? And okay, so the other thing is, and we have a little more discussion on that, maybe not in the next lecture is, okay, focusing on recurrent neural network, but in the next lecture in 1 week from now. So there are many, okay, there are many other approaches, okay, you can use, and okay, so just have a discussion in your group, and then maybe you can explain one more time, because we want to create some time series, correct?
Yes. Yes. So all the data that you would be given is batches of monthly data, right? So you do this hotspot discovery. You discover a hotspot for the first batch. Then you do it for you use a sliding window. So you do it for January, February. Then you do it for February, March. Then you do it for March, April. And like this way, you have a series of hotspots being discovered all throughout, right? So once you have that, that gives you a time series data, essentially a visual time series data of like how a particular hotspot may or may not change over the entire batch period. So once again, that is you analyze that change and then you write a report on it, like how that change is happening. If you can write like a manual report on it, or you can highlight it in you can create like a small demo to like show, for example, like a sliding bar that shows what is changing month to month to month. So you can do that, and you can submit the data as separately, or you can just analyze the data directly on your own as well.
So and then to kind of simplify the project, we basically, well, the idea is you just look at two kind of hotspots. One are pretty extreme hotspots. So for those, you would use a relatively high density threshold, correct? And there might be just isolated earthquake, or there might be very small regions. And then the second threshold would be like using the threshold of 3 or something like that. So one task of the project is, and that's not an easy task. So the idea is we want you to produce time series, but we don't want you to produce 500 time series, correct? But you have to find those two thresholds that allow you to create some time series of earthquakes, correct? And and then you get basically this time series, and well, and then you can just try to analyze it and just make some summary, correct? And you could, so this is okay, but the summary would be also now how the earthquake hotspots change, correct? And if they, and if now you could also write some functions that analyze the change, but this is, we don't expect this in the project, but it's something you can get some extra credit for. And then the other thing is we still have this idea, you develop this method, and at the end you get another data set that has exactly the same structure, but it might be crimes or some other things. And we want to look a little, okay, if you are able to reuse these techniques, and we just have to see how things evolve. So the other thing in this project, maybe in 2 weeks, each group can write a short status report, and depending on, okay, so there are a lot of optional things, and if you have some other ideas what you want to do in the group project, and ask us if this is suitable, then just, okay, ask us. So then they get 12 months of data, or how many?
24 months of data, but 12 batches.
Okay.
2-month batches.
Okay, so they're basically 21 time slots then. Okay, 23 time slots, correct? 23 windows. So are there any other questions concerning the goal of the project, or very basic things?
Okay, if there are none, then I'll stop sharing and Dr. Eick, you can take over.
Okay, so the one thing is maybe you can join us also in not the next lecture, but the lecture in 1 week. But I think we need to have a little more discussion about hotspot discovery techniques.
Sure, I will. Yeah, I will come back in. All right. Thank you, everyone.
Okay, so now, but this is kind of a continuation of what